Hey everyone, I am Priya K, Assistant Professor, Department of Integrated Chemistry, MES College, Marampally.
Today, we shall discuss the general characteristics of the D block elements. The topics today: introduction of the transition elements, the physical properties and the trends in the properties across D block. Why D block elements are called transition elements? Because they exhibit transitional behavior between S block and the P block elements, that is, between the highly reactive metallic S block elements which are ionic in nature and the non-metallic P block elements which are covalent in nature. There are 5d orbitals, the dxy, dxz, dyz, dx square y square and dz square. The transition and inner transition metals, the D block of the periodic table contains the elements of the groups 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods, and the F block consists of elements in 4f and 5f orbitals which are progressively filled. There are mainly 4 series of the transition metals: 3d, 4d, 5d and 6d series, and 2 series of inner transition metals, 4f series and 5f series, which are known as lanthanoids and actinoids respectively. These are the 4 series of transition elements: the 3d series from scandium to zinc, 4d series from yttrium to cadmium, and the 5d series from lanthanum and hafnium to mercury, and the 6d series actinium and rutherfordium to copernicium. The transition metals are defined as the metals which have incomplete deception either in their neutral atom or in their ions. But in the group 12, the zinc, cadmium and mercury, they have fully filled D10 configuration and they are not regarded as transition metals. Now we shall see the position in periodic table and electronic configuration. Here is the periodic table. As already mentioned, we can see the D block elements in the middle between the S block and the P block. And the 2 rows which are placed below the periodic table are the inner transition elements 4f series and the 5f series. The electronic configuration of D block elements. In general, the electronic configuration of outer orbitals of these elements is n-1 d1 to 10 and ns1 to 2. The n-1 stands for the inner d orbitals which may have 1 to 10 electrons, and the outermost ns orbital which may have 2 electrons. The electronic configuration of the outer orbitals of zinc, cadmium, and mercury and copernicium are represented by general formula n-1 d10 ns2. The d orbitals of the transition elements are diffuse, that is, they protrude to the periphery of the atom more than the other orbitals, and they are more influenced by the surroundings as well as the atoms or molecules surrounding them. Now we shall see the general characteristics. Physical properties. All the transition metals display typical metallic properties like high tensile strength, ductility, malleability, thermal electrical conductivity and luster. The transition elements are very hard and have low volatility except zinc, cadmium and mercury, and also their melting point and boiling points are also very high. Trends in the melting point of transition metals. We can see of all the elements in the periodic table, the tungsten in the 5d series is having the highest melting point, that is about 3410 degrees Celsius. This high melting point of these metals are attributed to the strong interatomic metal-metal bonding, and the strong interatomic metal-metal bonding results from the unpaired electrons in the n-1 d orbital and also the ns electrons. In any row, the melting point of these elements rises to a maximum at D5, except for the anomalous manganese and technetium here, and fall regularly as the atomic number increases. As the number of unpaired electrons in the d orbital increases, the strength of the interatomic metal-metal bonding increases, and hence the hardness and melting point also increases. And after d5, the number of unpaired electrons decreases and the strength of the metallic bond decreases, and hence the melting point and hardness also decreases. The trends in the enthalpies of atomization of transition elements. The metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series, which the great enthalpy of atomization of 4d and 5d is due to the metal-metal bonding in the heavy transition elements. Variation in atomic and ionic sizes of transition metals. The ions of the same charge in a given series show progressive decrease in radius with increase in atomic number. This is because the new electron enters a d orbital each time and the nuclear charge also increases by unity. And the shielding effect of the d electron is not that effective, hence the net electrostatic attraction between nuclear charge and the outermost electron increases and thus the ionic radii decreases. The same trend is observed in the atomic radii of the given series. The trends in the atomic radii of the transition elements. The variation within a series is quite small and there is an increase from in the atomic radii you can see here when in between the 3D and the 4D series of the elements. But the radii of the second, that is the 4D series here, which is in blue color, and the 5D series, which is in red color, this is almost same. This is due to the intervention of the 4f orbitals, which must be filled before the 5D series of elements begin. The filling of the 4f before the 5D orbitals results in a regular decrease in the atomic radii, which is called the lanthanide contraction. Thank you.